So, let's talk about chemistry. And I know, you might be thinking of complicated formulas and lab coats, but forget all that for a minute. Today, we're going to explore how chemistry is really the invisible architect of our daily lives, solving some of the biggest problems humanity has ever had to face.
Just take a quick look around you right now. Think about the stuff you use every single day. Now here's a question for you. What on earth could possibly connect the slick surface of your frying pan, the medicine that knocks out an infection, and yeah, even the plastic bottle you drink your water from? You might be surprised.
Yep, that's it. They are all just chemistry. Brilliant applications of chemistry, each one designed with a very specific purpose, to make our lives better, safer, and, well, longer. And that is the absolute core of what we're talking about today. Chemistry as this incredible tool in service of all of us.
Okay, so where do we even begin? Let's start with the literal world around us. For most of human history, we were stuck with whatever nature gave us: wood, stone, metal. But what if we could invent brand new materials designed from scratch to do exactly what we want? Well, that's precisely what chemists did. They kicked off a revolution with something called polymers.
Now, to get your head around polymers, you have to start with the most basic part, the monomer. The absolute best way to think about a monomer is like a single Lego brick. It's a small, simple molecule. By itself, it's not much, but it has all the potential to build something gigantic. And this little guy right here, this is one of the most important building blocks on the planet, the ethene monomer. Super simple, just some carbon and hydrogen. But you should not let that simplicity fool you. This tiny unit is the starting point for one of the most common plastics in the entire world.
So how do you get from that single Lego brick to a massive castle? Well, use a process called polymerization. This is really the chemical magic trick. It's where scientists create just the right conditions, the right temperature, the right pressure, to get millions of these little monomer units to link up, almost like they're holding hands, to form one giant chain. And this is exactly what that looks like. You see, we start with a huge number of individual ethene monomers. That N you see there, that could mean thousands or even millions. Then, after the polymerization reaction happens, boom, they're transformed into a single super long molecule, polyethylene, which you probably just call polyethylene. The simple brick becomes a strong, flexible wall. But of course, chemistry gives us options. There are two main families here. You've got homopolymers, like our polyethylene, which are made by repeating just one type of monomer. Think of it like building with only red Legos. Then you have copolymers, like nylon, which are made by alternating two or more different monomers, like using red and blue Legos to create a totally new pattern with totally new properties.
How those blocks connect is also a big deal. In what we call addition polymerization, the monomers just add to each other, clean as a whistle, no leftover pieces. It's just like Legos clicking together perfectly. But with condensation polymerization, it's a bit different. When two monomers join, a tiny molecule, usually water, gets kicked out. It's more like gluing bricks together, where a little bit of glue might squeeze out from the seam. Now, let's look at a classic example of that condensation process. I know, this reaction looks a little complicated, but what it's showing is the creation of something amazing, bakelite. This wasn't just another new material. When this was invented in the early 20th century, it was a massive breakthrough. For the first time ever, chemists made a material that had absolutely no equivalent in nature.
And the impact of that? It was huge. Bakelite was the world's first fully synthetic plastic, and that meant it freed us from the limits of what we could dig up or chop down. All of a sudden, you could make a durable comb that wasn't carved from expensive ivory, or an electrical switch that wasn't made from wood. This stuff, born in a lab, literally shaped the modern world, from old radios to the very first records that brought music into people's homes.
Okay, so from building our world, let's pivot to healing our bodies. The next great challenge chemistry took on was our age-old battle against pain, fever, and disease. And this is where chemistry gets really, really personal.
What chemists did was develop a powerful toolkit of molecules, each one designed to interact with our bodies in a very precise way. We're going to look at three of the most important tools in that kit: analgesics for pain, antipyretics for fevers, and the game-changing antibiotics for bacterial infections. A lot of us have probably taken drugs that do double duty. Analgesics work to relieve pain, often by targeting our nervous system. Antipyretics, on the other hand, work on the brain's thermostat to bring a dangerous fever back down. And pretty often, one single, elegantly designed chemical can do both jobs at once. And this molecule right here is probably the most famous drug in history: acetyl salicylic acid. You almost certainly know it as aspirin. For over 100 years, this relatively simple little structure has been the go-to for relieving headaches, pains, and fevers for billions of people.
It is truly a marvel of medicinal chemistry.
But what about when the problem isn't pain or fever, but a microscopic invader? Well, that's where antibiotics come in. It's hard to imagine, but before these chemicals, a simple infected cut could easily be a death sentence. Antibiotics are chemicals that can kill harmful bacteria without hurting our own cells, a life-saving distinction.
And this is the structure of the one that started the whole revolution, penicillin. Its discovery didn't just change medicine, it completely changed our definition of what was survivable. It turned deadly infections into treatable conditions. It made modern surgery possible. I mean, its impact is almost impossible to overstate.
Okay, so we built a better world, and we've learned how to heal our bodies. But there's another absolutely fundamental challenge. How do we feed everybody? With the world's population growing and growing, we had to find a way to make our farmland way more productive. And once again, chemistry answered the call.
The first part of the answer is fertilizers. Think of soil like a pantry for plants. Every time a crop grows, it takes essential nutrients out of that pantry. Well, fertilizers are just a way to restock the shelves, adding back those key chemical elements that plants need to grow strong.
And when it comes to plant food, these are the big three. Nitrogen is what they need for leafy growth and that healthy green color. Phosphorus is all about helping establish strong roots and making sure the crop matures on time. And potassium, well, it acts kind of like a plant's immune system, helping it fight off diseases. By managing these three, farmers can get so much more out of their land.
But growing more food is only half the battle, right? You also have to protect it. And that's where the other side of the coin comes in. Pesticides. These are targeted chemicals designed to defend crops from all the things that want to eat them. Insects, weeds, fungi, anything that could wipe out a harvest.
So, we've taken a quick journey through materials, medicine, and agriculture. Let's just take a step back for a second and think about what this all means for us today and for where we're headed.
You know, when you connect all these dots, the conclusion is pretty obvious. The story of our modern world is completely tied up with the story of applied chemistry. The synthetic stuff building our world, the drugs healing our bodies, and the agrochemicals feeding us, these are the pillars that support the longer, healthier, more comfortable lives that we live today. So we now have this incredible chemical toolbox, and we're capable of reshaping our world all the way down to the molecular level. So as we look ahead to the huge challenges of clean energy, of climate change, of new diseases, it leaves us with a really important question. With all these powerful tools, what's the next great problem that humanity is going to solve with chemistry?